Hello, and welcome to the Geopolitics Explained podcast. In the last episode, we started the series on game theory that we'll be pursuing for this month. We covered my introduction to game theory, as well as discussing some games and its connections to geopolitics that we can model through game theory. Today, we're going to pivot more towards the mathematical side of game theory. To begin this, I'm going to discuss one of the simplest games that we can use to model probabilities and mathematics in game theory, and that is rock, paper, scissors. Now, in a two-player game of rock, paper, scissors, the probability of you winning is always a third. If we go through every scenario, if you choose rock and your opponent chooses rock, then you draw. If you choose rock and your opponent chooses paper, you lose. If you choose rock and your opponent chooses scissors, you win. We can also repeat this process for you choosing paper, and we can repeat it once again for you choosing scissors. The three results from choosing each of the three of rock, paper, scissors is one scenario with a win, one scenario with a draw, and one scenario with a loss. As a result of all 9 scenarios, in 3 of these you win, hence the probability of 1 out of 3, or 33.33% recurring. This is an example that we can explain via brute force by plotting out every potential scenario. But in considering the mathematics of game theory, calculating probabilities can get more difficult as the complexity of the game increases. With this being said, let's consider poker. In a game of poker, each player is dealt 2 cards, and 5 cards are dealt by the dealer onto the table face down. Over time, these 5 cards are revealed, and each player uses the best 5-card hand out of their 2 cards and the 5 cards on the table. To calculate the total potential number of different 7-card combinations, we use a mathematical tool called the binomial coefficient. This can be used in any game to calculate the total number of potential scenarios. If anybody owns a scientific calculator, the binomial coefficient is represented by the NCR button. In the example of poker, there are 52 cards and we draw 7. So the input would be 52, NCR 7. This provides 133,784,560 possible 7-card arrangements. This is slightly more complicated than an example of rock, paper, scissors. Poker is a great demonstration of how complex games can be. We can calculate the probabilities as we're sat down with a piece of pen and paper thinking about it, but in an actual game moving in real time, calculating this in your head is close to impossible. Online poker has seen the creation of calculators that can figure out the odds of a hand winning a game, and so they can be used in online poker games, but typically this is a pursuit that is difficult to undertake. So now that we've discussed 2 games and highlighted how more complex games can make modelling these games mathematically more difficult, I'm going to introduce a concept that could aid in modelling these complex games. This is called expected value. Expected value is the expected payout from an event. Let's say we have a normal coin with heads on one side and tails on the other. If the event that we are expecting is for the coin to land on heads, then the probability of this event occurring is 1/2. Let's say if the coin lands on heads, you receive a payout of £10. Your expected value would be the probability of the coin landing on heads, which is 1/2, multiplied by the potential payout, which is £10. In this scenario, the expected value would be a half times £10, which is £5. Now, we can also expand this scenario. Let's say you bet on the coin landing on heads again, but this time, if the coin doesn't land on heads, you lose £7.50. This scenario will unfold as follows. We consider the first scenario, that the coin lands on heads first. We've already modelled this. To calculate the expected value of this, we times the probability, which is a half, by the payout of £10. So the first term in this expected value calculation is £5. But now, if the coin doesn't land on heads, we lose £7.50. The probability of the coin not landing on heads is also a half, because this is the probability of the coin landing on tails. We times this by the potential payout, which is minus £7.50, and this equals £3.75. So, the expected value of a win is £5, and we take away the expected value of a loss, which is minus £3.75. From this entire scenario, this gives a total expected value of £1.25. The most important aspect here is that this is a positive expected value. If the loss was £12.50 every time you didn't land on heads, the expected value would be negative £1.25. A negative expected value would mean an average loss over time. An expected value of 0 would occur by not taking the bet at all, and so this would be the preferred strategy if the total loss every time you didn't land on heads was over £10. Poker expected values are a lot more complicated due to the differences in every round and the sheer complexity of the number of potential hands that can emerge. In poker, we can calculate probabilities using Bayes' theorem. I will discuss this later on, but for now, we're going to move on to discussing some more mathematical terms that can help us in modelling games. The next term that I want to discuss is variance. Variance is connected to the expected value. Variance describes the potential spread of possible outcomes from the expected value. In the previous example, where we had a £10 payout if the coin landed on heads, and a £7.50 loss if the coin landed on tails, we had an expected value of £1.25. The variance will measure how far the results will spread from the average. The next term that I want to discuss is distribution. A distribution gives the possible values from an event and the probabilities for how often they occur. The statistical distribution that can be used to model a game depends on the characteristics of that game. The final term that I want to discuss is utility. Utility describes an individual's approach to a game as they measure the value of each possible decision that is involved in the game. The optimal decision is the one that expands the expected utility. In our previous example, the expected value was £1.25 on average over time. If you ever find yourself above this value, it would make sense to take your winnings and run. The general theory of utility is that the more you get, the less you gain from any extra input. The theory of utility works in many fields, not just in mathematics and game theory. Let's say you love a certain food, so you buy this food every single day. Over time, you will reach the point where the enjoyment gained from eating this food is practically zero. In fact, the utility could even be negative due to the effort of dealing with the sheer number of packets of this food that you might possess. In poker, utility is slightly more difficult to determine. There are many players, and calculating the probabilities of different hands occurring is difficult. This also introduces the psychology of game theory, where bluffing could be introduced. Of these characteristics that we've discussed, expected value is the most important, but determining utility in relation to the expected value is also a key tool that we can use when exploring mathematics and game theory. In relation to mathematics and game theory, the next issue to discuss is risk. Risk of ruin describes the probability that an individual will lose such amounts of money where they reach the point that recovering from their losses is impossible. This can be seen in trading, in investing, or in gambling. Risk of ruin is typically calculated using value at risk. Value at risk is a statistic that places the possible financial losses into a numerical value. It does this for a specific time frame and with a certain probability of confidence. In investments, value at risk shows the potential loss that an asset could experience over time. Investments also feature a standard deviation. This can show how the returns of an asset can vary over time. So, standard deviation can measure volatility, and a higher standard deviation means that an asset is more volatile and riskier. Outside of value at risk and standard deviation, another measurement of risk is expected shortfall. Expected shortfall is considered better than value at risk because it describes the conditional expectation of loss, given that that loss is beyond the value at risk level. So, if we first calculate value at risk, the expected shortfall is the expectation that we experience a further loss than the level that is calculated by value at risk. So this measurement will appeal to those who have a low risk appetite, who want to ensure that they won't be ruined in whatever game they are playing. Now, there are ways in these games that we can reduce risk. This is done by avoiding the risk of ruin and by minimizing our value at risk or expected shortfall. We can do this through the Kelly criterion. The Kelly criterion details the maximum bet that should be made in a specific game. It is commonly used in asset allocation models and investing, in detailing how much capital to allocate to specific opportunities. The Kelly criterion is the following formula. We take W, which is the probability of winning, and we take away the probability of losing divided by the win-loss ratio. Another useful term in modelling risk is risk aversion. Every person in a game has an individual level of risk that they are comfortable taking. If you are risk averse, you prefer a higher probability of success, even if this is coupled with a low payoff. If you are risk tolerant, you are more accepting of risk and hence could pursue a higher payoff. This is evident in investing. The older, retired generations typically invest in bonds and precious metals. This is because these assets provide a small, steady, positive return for many years. If you look towards younger generations, these are typically the generations who are seen more actively in the cryptocurrency sector. This is because crypto provides higher returns, but that is coupled with higher risk. So there are many mathematical tools that we can use to model games and game theory. These concepts would translate over to other games that are mathematical in nature. But in collecting all this together, we need to return to a concept that we discussed in the first episode, and that is the Nash equilibrium. To return to what we discussed last episode, the Nash equilibrium is the set of strategies that are the best strategies for every player. As a result, in this scenario, no player is incentivized to change strategy. Now, the Nash equilibrium in games depends on the characteristics that we discussed in the introduction, those being the number of players, the strategies, the number of potential Nash equilibrium, whether the game is sequential, if players have perfect information, if we have a constant sum game, and if the game contains random moves by nature. However, in exploring the Nash equilibrium, we are assuming that all players are rational. This will set up what we'll discuss next episode, which is the psychology of game theory. That's all for today. If you enjoyed this episode, please consider leaving a review on the podcast platform of your choice. I've been Dylan, and I'll talk to you next time.